Today we move a rope around a grid. For part 1, the rope consists of 2 knots, and for part 10 of 10 knots. Here's a list of directions where the head shall be moved and the tail must then follow. And I first unroll those directions by basically simply repeating those numbers, right? So R4 turns into 4 repetitions of going right. That's +1 in the x direction. Going up 4 times is -1 in the y direction, and so on. Okay, so a simple reseq that searches for LRUD followed by a number. Then we destructure into the whole group the character LRUD and then the number. Of course, we have to pass that number, and then we can use the repeat function. Okay, and how do I turn the character into a direction? I simply use a hash map. Well, there's a hash map, right? So I convert LRUD to the corresponding vector. Okay, and the key that I use to look up is the first character in my string. So one of those 4 characters. Right, then 2 helper functions that will come in handy later for adding 2 element vectors and for subtracting 2 element vectors. And then if we look at the rules carefully, it tells us if the head is ever 2 steps directly, up, down, left, right from tail, the tail must also move 1 step in that direction. Those are these moves here. So the key is the delta between the head and the tail, and the value is the force applied, or how much do we have to move the tail. Okay, and here the second part of the rule is about diagonal. So if we are here, the distance is only 2, and here the distance is 3. In those cases, we have to move diagonally. Right, and then the code for part 1. How many positions does the tail of the rope visit at least once? So we start with the head at the origin. The tail is also at the origin. They share the same immutable vector. Visited is an empty hash set. And here we unroll the directions as explained above and immediately destructure into the first and the rest of the directions. Then we note that we have visited the tail by rebinding visited to a nested binding that shadows the outer one. And if there are no more directions, then we simply count how many are in the visited hash sets, and duplicates will be rejected automatically. So only the unique ones will be counted. Right, then here we move the head with a shadowing binding. Then we calculate how far is the head from the tail. Then we look up in the dictionary what's the force according to that delta. And that may be nil if head and tail are still connected. Only if they are no longer connected, we get a non-nil value. Then we actually apply the force to the tail. Otherwise, we take the tail as it is. Yeah, and then we recur. Right. So not too hard. Then for the second part, we have more forces. Apparently, lots of people didn't read this sentence. So now it's possible that the delta has a distance of 4, and in that case, we also shall move diagonally. That's just 4 additional key value pairs in comparison with the forces 1. Okay, and then I built a recursive helper function. Maybe let's look at this example. Let's say the rope has only 5 knots, and we already moved the A1 to the left, and now here is a gap. What do we have to do? Well, first we have to move the B over, and then we have a new situation that looks similar to the one above, just with one shorter rope. And then via recursion, we can call ourselves again and again until we finally solve the total problem, right? That's the magic of recursion. Solve part of the problem and then invoke yourself again for the smaller rest of the problem. Okay, so the A in this diagram would be the moved head. That's already moved. That's why I called it that. Then B is the first tail that we maybe have to move, and CDE is the rest of the tails that we don't touch in this recursive invocation, but maybe in the next ones. Okay, and this syntax means the entire undestructured parameter shall be named rope. So rope is the entire thing here, basically. Okay, if there is no more tail, then we are done. There's nothing left to do. then we can simply return the rope as it is. Otherwise, we compute a delta again, similar as we did here, just with slightly different names. Then we look up the force again, this time in the slightly larger hash map. And again, if there is no force to apply, then there's nothing left to do. We can return the rope as it is. Okay, otherwise, what do we do? So first we apply the force to our first tail. That will move the B over, basically. Then we cons it onto the more tails. Then we have a shorter rope without the A, basically. And there, this is what we pass to the recursive invocation. And once that problem is solved, that will be this guy, basically, then we can cons the A back on. And that's why we do that last here. Okay, yeah, and then part 2, which will use the recursive follow function. So it looks quite similar first. So here head and tails is a bit different. Now they are not two distinct variables. We simply destructure a list that starts out as 10 0 vectors. Here you are. The rest of the variables is the same. The visited is similar. Here we're only interested in the last tail that also trips people up. So only the E in this diagram, if you will. And then this is slightly different. So here we compute the new head, and then we cons the new head onto the old tail. So this is basically the movement of A1 to the left, if you will. And then we call follow for the very first time, and that will follow all the tails. Yeah, and then we recur again until the directions are completely exhausted.